excited to be here because I don't know what's going to happen here. So it's rare that you go to a workshop where you don't know what's going to happen. So I'm here to tell you a story about my interest in evolution, which has come through studying machine learning. And there are a few other people who have contributed also to this viewpoint, listed here, who are also going to speak, I think, in that order. So since we're asked to be provocative, that's one thing I'll fulfill. So at a very general level, you can ask, why do people come into this field from somewhere far away? And so one question is, how is Darwin's theory doing? And I think we all believe that evidence for it is overwhelming and increasing rapidly, and it's an amazing theory. But there always has to be a but. And the but is that there's still some people with some kind of unease, and the unease always comes from the fact that simply the standards of explanation that we require are kind of increasing every day. So things which were okay 100 years ago, now we want better explanations. There are always questions we personally want to ask, which we don't know the answer to, and one has to re-ask these questions again. And there are two main sources of these higher standards. So one is computation, and the other is biology. So I don't know what Victorians thought, but maybe if they realized that if they suggested mechanisms, then I'm not sure whether they realized that maybe so many years later people would be able to actually simulate these mechanisms on a computer and actually see what happened. So this must be a frightening, must have been a frightening prospect for them if they were aware of it. So in every other science, we simulate the predictions of the science and things work out. I mean, does that happen in evolution? And my kind of tentative answer is no, because people have tried to simulate what they think was Darwinian evolution from the 1940s onwards. And at least in my view, lifelike phenomena are hard to find in computers. So saying that Darwinian evolution has been verified by amazing simulations, I think, would be an overstatement. And I think this is a problem because the lack of computer power is getting less and less of an excuse. And the question is whether, is this direction becoming increasingly more and more embarrassing for evolution, in that if every other science can simulate its predictions, why can't this? And the other source where I think one demands higher and higher standards is biology. So things, again, which weren't known a long time ago, is that biology is extremely complicated. If people try to trace the signaling pathways in biology, you get vast numbers of these diagrams, which are very hard to understand. So the reason why computer simulations may not be doing what we hope is because there is a theoretical problem to overcome, which we haven't. So if biology is complicated, we know the DNA is many bits, billions of bits. If it really takes billions of bits to describe, then how could it have arisen in time, say linear, in this billion bits? Only a billion years. Now, of course, there may be many generations in a year, and there may be many individuals in a population, but whatever you do, you need to get an explanation for evolution which is not exponential. Okay, so if your best explanation for how something, a complex function organ, can evolve is exponential in the length of description, then you're in trouble. You're nowhere. And even if you say that the number of bits in DNA which is important isn't a billion, but even a million, that doesn't change the argument. Okay, so it seems that one does need to have any theory of evolution and something which encourages to have confidence in simulations. You need some polynomial type story. So how can something evolve in time, polynomial in its description? Okay. So that's where we're going. And also from biology, biology points us very definitely to what we should actually investigate. It's less of a mystery than 100 years ago. So we differ from trilobites by lots of mutations. Any theory which doesn't account for what mutations do doesn't work. So we have to explain mutations. And also we know what biology does, that most basically your DNA describes protein expression. Okay, so your DNA is a protein expression network description. Okay, so somehow biology tells us very definitely at what level we should explore our algorithms. So what we need to do is to explain quantitatively how protein expression circuits can make themselves fitter by mutations and selection. So the only important word here is quantitatively, that one wants a theory which explains how in numbers of generations and populations which are reasonable, you can make progress along Darwinian principles. Okay, so biology tells us at what granularity evolution occurs. And if one wants to even put a sharper point on it, so we have genes, they express proteins, and what's important is how much they express. At each instant, a gene can decide how much protein to express, and that depends on some function of the concentrations of other proteins, other chemicals, etc. Okay, so what your gene does, it computes a function. It expresses something at a certain level, and it depends on the concentrations of stuff around it. Okay. And so if we believe the rough summary I gave, then one somehow wants an explanation of how Darwinian evolution works at this level. So we get individual mutations are clearly important. Other stuff happens in biology, but individual mutations seem to enable these functions to get updated by Darwinian principles, which means increasing fitness. So I'm saying that biology tells us at what level we should look for an explanation of evolution. It doesn't have to be some ethereal level. Okay, so what I'm interested in is some sort of complexity of Darwinian evolution, and the important concept is that what's evolving is a function, and in biology the function is the expression function of individual proteins, and this function is some function. It depends on some parameters, the concentrations of other proteins, and it's some function. It may be this, it may be a polynomial function, it may be a Boolean function. What kind of function is what we need to determine. Okay, and so the question is, if this is what you have now, how can this function change? How can it adapt to be fitter under the Darwinian process? Okay, and the usual conundrum is that if you decide that this function is a very rich class, all functions, then you find it very hard to find an algorithm which can navigate it. Whereas if the function class is too weak, like all the functions are one variable functions, then it's not rich enough for biology and doesn't explain anything. Okay, so you want the kind of biggest functions. So how can anything I've said be wrong? Well, one way in which it can be wrong is that it may just be impossible to carry out, and maybe that's the standard answer at this point. Because, so I'm serious about these things. I want to evolve functions, I want quantities, I want to model what fitness is, and I want adaptation. I want an algorithm which adapts these functions, and I want to explain everything. But, of course, the problem is that some of these things are hard to model, and in particular, fitness of your genotype is very difficult to evaluate by looking at it, because its connection with the phenotype, the environment, and the ecology, it's all related, and we don't know what it is. And probably the evolution algorithm doesn't know what it is either. So, so how is it possible to have a theory of this without understanding how your DNA, what makes the DNA fit? Because understanding how the DNA is fit would involve all kinds of knowledge which we don't have. And the evolution algorithm doesn't have either. Because how is this possible? Okay. So this is the main point. that, so what I want to show is that using ideas in learning theory, you can model everything you want, and you don't need to model what you don't want, what you cannot. Okay, so in particular, most crudely, the point is that you have learning algorithms which can learn to translate English to German, but these algorithms don't understand what they're doing. Okay, so the claim is that evolution works the same way, that you can, in the same way that, that a learning algorithm doesn't really understand what it's doing, evolution doesn't either. Okay, so let's just quickly refresh what.
Ask you, so, I mean, the translating English to German, it knows what there is something that it's trying to do. I thought part of the problem here was that it's not clear what the goal is.
Okay, so yes, great. I'll address that point. That's an important point. Okay, yes, okay. Okay, so there's a slightly different what I said for my point. Okay, so there's 1 minute of what a learning algorithm is. So in a learning algorithm, you get some examples. Say maybe the dimensions of a flower. The flower is 1 centimeter long, 1 centimeter wide, etc. And it's described as a positive example of certain species, and this one is a negative example. So you want to learn to recognize future examples of this flower. So the perceptron algorithm maintains a linear separator. So it's a linear function of the three measurements of the flower. And what the algorithm does is that it starts with a hypothesis, it sees an example, and it changes the hypothesis. So in this case, it simply added the 1, 1, and 2 to the 3, 4, and 7, and minus 7 to get this. And the reason it did that was that if you substitute this into that, then this hypothesis would have misclassified this example. And if you misclassify an example in one direction, you just add the example. And in the second one, you got this one from this one by subtracting the example from the coefficients. Okay. And so the details don't matter, but this learning algorithm does some pretty trivial-looking changes. And if you looked at the learning algorithm proceeding, you think it's kind of some random nonsense. But the whole point is that you can prove that this algorithm has some good convergence properties. Eventually, it's going to do pretty well. So the idea is that this algorithm has a plan. Okay, this learning algorithm has a plan. It knows what it's doing. It doesn't seem to know what it's doing, but it does. So as far as the goal, I think this is an important point, that so a learning algorithm has a goal of converging and being able to predict better. I mean, so using the word goal in evolution is very politically incorrect. But what we need to look for is something very similar, that there must be a mechanism which for some reason doesn't make progress. It's kind of, there's a reason why it works, there's a reason why it improves. And saying that evolution has a goal in this sense is innocuous. A goal doesn't mean in the sense that there's someone who is driving somewhere. Okay. Just one other comment is that standard learning algorithms are extremely Lamarckian in that a single example can change your hypothesis. Okay, so the correspondence between learning algorithms and evolution are making is, I think, the kind of the obvious one. So in learning, you have examples, flower, not flower. So individuals in a species have experiences. In learning, you form a hypothesis. Individuals have genomes. So both of these are kind of functions. So the hypothesis, given an input, says yes or no. It's a function. And the genome, again, is a function. It tells, for various combinations of protein concentrations, it tells each gene how much to express. So you're learning functions from examples. So you've got a learning algorithm, like the perceptron algorithm. So the main part of an evolutionary algorithm is just the mechanism for variation. So how do you produce variance? Then they're somehow evaluated and there's selection. But the main algorithmic issues is how do you produce variation? Okay, so the fourth part is what's the reality check on these things? What's the feedback from the real world? So in a learning algorithm, you see examples, you classify it one way or the other, and then you're told whether you're right or not. Darwin tells us that the feedback in evolution is survival. Okay, so you go through this process, but the only reality check is survival. Okay, so you change this, try this genome, try that genome, you survive or not. Okay, and I'll say that that both have the same goal, which is improvement. So certainly in learning, you want to improve the accuracy with which you predict, and in Darwinian evolution, I'd suggest, although it's not the usual terminology, is that Darwinian evolution does have a goal, and that is to increase fitness. Okay, so basically Darwin says that, or Darwin implies that, actions have consequences. So whatever we do, whatever our genes do, some are better for us, some are worse for us. And if we do things that are worse for us, then we'll survive less often. And the effect will be that we'll have improved, we have an improvement in fitness. So just like in a learning algorithm, no one questions that a learning algorithm has a goal of increasing the accuracy of predicting something. In the same way, I don't think anyone should quarrel that evolution has the goal of increasing fitness. So if you believe that fitness makes sense, then you have to believe that the goal of evolution is that.
Okay. That might be kind of an empty hypothesis then, though.
Sorry?
That might be kind of vacuously true there, though. I mean, fitness making sense is a
well, okay, so...
Can I ask you to define fitness?
Sorry?
So can we ask you to define fitness?
I will, yes, I will. That's the point. Okay, that's the whole point. Okay. Okay, so quickly, so some other speakers will be a bit more formal, I'll be informal. So again, with the issue of goal, so Darwin says actions have consequences, and so I discussed this notion of ideal function, which I think isn't the best choice of words. If I choose it now, I'd say a kind of better for you function. Ideal sounds too good. But the idea is that in each circumstance, should you bring a cup of coffee into this room now, things like that, there are better things to do and worse things to do. Okay, and so Darwin says that it matters which one you do, and I'm saying up in the sky is written for every possible combination of inputs, maybe for every possible combination of concentrations of your proteins, the best level at which to express your protein at this instant. So in every situation, there are better and worse things to do. This is just a description, ideal description of the better thing to do in every possible situation. Okay, so if you believe that the better actions and worse actions for you, then you can't dispute this. Yes, just saying in every situation, there's an evaluation of how good it is for you to do different things. Okay, that's all. Yes.
Sorry, you're including in these situations also the rest of the population.
So the view taken here is that the rest of the world is fixed, and there's some evolving entity, and for this evolving entity, what's the best for survival? Okay.
Is there just a single best thing to do, or is there a multiplicity possible?
Well, in each situation, maybe you can do 25 different things, and there's some ranking of what's better and what's worse.
But there's always one at the top.
Well, no. Okay, no. Maybe they're all the same. Maybe no one cares which one you do. Okay, in one particular circumstance. Okay, so ideal is just an evaluation of how good various things are. Okay, so.
Is it crucial here that the rest of the world is fixed?
Well, yes. So if you want to study the dynamics, then other people do that. Okay, but I don't study dynamics. Okay. Because there's some basic problems which I think you have to start simply, and this is the only way to do it. Okay, so this is the specification of what are good things to do. Okay, so you want to evolve, want to get better and better in that direction. The other important point is that is that the learning algorithms I'm going to use have to be constrained. So Darwin tells us pretty specifically what's allowed as a learning algorithm, and it becomes quite a nice formalization if you formulate it in machine learning terms. So basic idea is that the variants you produce, there's a current genome, and the variants you produce have to be produced independent of experience. Then you let them out in the world, and then they test themselves against experience, and the better ones win, or the best ones win. Okay, but you can't. Your current experience can't influence which variants you produce. So this is like maybe a purist Darwinian view. You may want to make up other intermediate models, but it's hard to see what they would be. Okay, so we limit machine learning algorithms to be Darwinian. So this is certainly the case. We have to do. So how the variants are produced? So it's very hard to get evolutionary algorithms which do anything. So in the first instance, we're very generous. So we allow any process which is kind of computationally possible. So you've got your genome. What can a polynomial time randomized Turing machine do? You can certainly flip a bit. It can certainly do a single mutation. You can copy a whole bit of tape somewhere else. It can do various other things. So it's very, very, very powerful. But the point is that even if we allow this, it's difficult to think of how you should produce variants which are really useful, which really explore the space. Okay, so part of the study is to figure out, maybe whether there are exotic evolutionary mechanisms which do more than we can imagine. And then the other main thing is that we want to keep honest quantitatively, so the population sizes will be limited, the number of generations will be limited, and each individual will have limited numbers of experiences. So nothing will be exponential. Okay, so these are kind of the rules of the game. And one can formalize this in various ways. And so one can look at real valued functions, one can look at Boolean functions, one can look at hybrid models, and some speakers will discuss that. But just to, so the point I want to make now is that the important point is that fitness, what is fitness? I want to explain that fitness has to be defined. So the ideal function, okay, so this is your, okay. So the ideal function is, so if your genome expressed at this, something at this, according to exactly this function, that would be the best. Let's suppose that. And why this function is good depends on all this complicated stuff about ecology, environment, everyone else, but we don't have to know that. That's outside the theory. That's one good thing. Now the inputs come from an arbitrary distribution because the world is complicated. We can't assume anything about that. So the values can be, you can have different values for x1 and x2 which occur in nature. Some are more frequent, others are less so. Now your current genome isn't the best one, is this. So if it, to the extent it departs from it on a particular input, it's not going to be the best. So it's going to suffer some loss. And exactly, how much you pay for doing the wrong thing is depends on the situation. But supposing it's just a difference, that's just an example. But of course, in the real world, if it's best to drink 3 cups of coffee a day and you drink 30, then the question is how should you be penalized? Is it linear in the 27, square in the 27, or whatever? So we don't know. So we have to be robust in that as well. Okay. But then, given this, one can define a notion of fitness. So I call it performance. Okay. So basically, so you've got all possible circumstances you can encounter, the values of these variables. And there's some distribution. So some are common and some are not common. The uncommon ones are less important. And then your performance is like how much worse you do over all the examples weighted by the examples. Okay. So this is a definition of fitness. Okay, so if you tell me the ideal behavior and the real world distribution, then together, and there's also a loss function, then together it will define the fitness of any G. Because you just say, on the average, how much worse do you do than the best behavior?
So this fitness is the expectation of the number of surviving offspring as well.
No. Okay, so
That was the earlier definition.
No, okay, so this is different. So I think the
Yeah.
number of surviving offspring, I think that's a circular definition, okay? Okay, that's, so when the notion of fitness was suggested in the 1860s, the survival of the fittest, I think the meaning was that we're fit in different ways, and because of our characteristics, we have more or less fewer offspring. Then subsequently, people started defining fitness in terms of the number of offspring. But I want to go back. Okay, I really want to explain what makes someone have more offspring.
Yeah, but you still have to have the offspring in there. You're saying the performance equals number of offspring.
No, the performance is I'm defining a notion of fitness. Now, this will correspond to the number of offspring, but okay, I'm not quite sure what that correspondence is. It doesn't have to be equal to that.
You have to have a mapping from performance to probability of having offspring.
No, you could talk about that the performance is how long is it before your older descendants go extinct, which is not directly related to number of offspring at all.
Right. Okay. But okay. So the main point is that so if you believe that fitness is something, I mean, if you believe fitness is just some accounting method of counting how many offspring you have, then okay, then be happy with that. But I think the notion of survival of the fittest means something more. It means that depending on what we do and who we are, what our genome is, we have better or worse. There's an explanation of why we have more of your offspring. Okay, so if you really believe that fitness isn't just a population metric, if you think that fitness is has some factual correspondence to how you perform, then you do this. So I call this performance rather than fitness, just to avoid this contradiction. So I'm calling this performance. Let's forget.
Do you have examples of loss functions that don't refer to the ideal function?
No.
Because doesn't that bake in something that evolution doesn't know into your dynamic?
Well, but I'm saying the evolution does know the ideal function, in the sense that, in the simple sense, we don't know it. But if you send out individuals, then the ones whose behavior departs from the ideal function survive less often. So the ideal function no one knows, but you discover it by, if your behavior is very different from it, you'll die. You'll find it out implicitly by survival. Okay.
So the ideal function is basically an output based on multiple inputs, all of which are concentrations of proteins?
Well, you can take
that.
So whatever the evolving entity is, yeah. So if you're just interested in proteins, yes, it's the ideal function describes for all your proteins.
So it doesn't change over time.
So what the ideal is depends on. Okay, so we'll define this ideal for, say, one evolving entity, say humans at this instant, with a certain ecology, a certain environment. Certainly, if the climate changes or other predators appear, then we may have to change. The ideal function will change. So the ideal function is something, the causes of it are extremely complicated and things we've got no chance of understanding. But it's too big to write down for a start, and what determines it are stuff we don't understand. It's to do with phenotypes, genotypes, etc.
But implicit in your argument is the fact that whatever is evolving has not yet achieved the ideal function, right?
Yeah, well, of course, the ideal function can change. The whole point is the ideal function will change. As you know. So this is very much centric to the evolving entity. So if other species arise, climate changes, ideal function changes. Okay.
Yeah, so if you have niches, you should have multiple ideal functions, right?
Yes, so the full model is that each gene, it's a cross product of all these ideal functions. If you've got many proteins, yes.
I'm just wondering if one can just abstract away the stuff about concentrations of proteins, because it seems like you're going from, can't you just go from experiences, which is the input to this function, down, and talk about, well, what's the genome, and just have a function that goes from, the genome to how it deals with particular experiences. Why is it necessary to have that extra step of proteins?
Well, I think you can do it at any level you choose. Okay, so maybe my words I use I'm changing my levels, but certainly you can choose it at the level of the expression of proteins. So the ideal function can be defined just for protein expressions. Okay.
So the ideal function is set only by the abiotic environment. There's no frequency dependence, no density dependence. There's no, well, there may be other species involved, but there's nothing from within the species itself.
Well, it could. I'm not telling you. It could be determined by anything. Okay.
Including what other functions are present, what other genomes are present at the current time.
Sure. Yeah. Yes. Yes. I mean the way to view it is that so your protein does have some little function which describes its behavior, okay? And it is chosen from some class. So what I'm saying here is, and the question is, some may be better for it than others. And whatever is the best, I call the ideal function, okay? And what the ideal function depends on, I don't want to know. It's very complicated. Yes?
So this performance function, I agree it's going to be calculated in the real world, but it could take a long time.
To calculate?
Yeah, over many generations.
Yeah, okay. So then I haven't given you the full definition yet. So this will be an empirical value. So in evolution, an individual will only be able to compute this, not by computing the ideal expected value, but by just having a limited number of experiences. And it will be the expected value over a polynomial number of random experiences. It's an empirical expectation. Okay, so...
It could also, well, it's probably the same what I mean. It could take many generations to really find out whether the genome is good in this world.
Yes, but what will happen will be determined by how good the genome is on the number of experiences this individual is allowed to have. And that is also a model, that you don't take this value seriously to the extent that you need too many examples to find out the exact value. Okay, so it's an empirical thing. Okay, but I think the main point is what this argument is circling around, is that I really think that one needs if you believe fitness is real rather than just a population counting statistic, then you need some definition of fitness in terms of other things. And so here the fitness depends on what the best behavior is, and it kind of depends on aspects of the world, largely encoded by this ideal behavior. Okay. So fitness. The picture I found on just the curve is what you see on Wikipedia, which I don't fully understand. So for me, fitness is determined by this ideal function and drawn from a distribution, or by a loss function, and it means that for every genome, I can attach a numerical fitness. Okay. Now, what the word landscape means, what's next to what you can reach easily from what. I mean, that's more complicated, because that's kind of what one tries to explore. So in a learning algorithm, you represent different genomes in different ways, and the algorithm, the method of variation, knows from which representation it can easily go to next. So, so very roughly, but what's going on is that what one tries to show is that for simple enough functions, the fitness will have a landscape which is a fitness described the way I described will have a landscape which is explorable effectively. Okay, so for certain simple functions, evolution works, And if you make it too complicated, it won't. Okay, so very quickly, as far as examples of results. So this genome expression function is probably something simple. So this could be, it's a Boolean function, this one. You've got 20,000 proteins, and it's good for you to express this one if either the first, third, or seventh is in the soup. Okay, so that's one possible expression function. And another one is same thing, but it's good to express something if an odd number of these three are true. So these are very similar functions. But it turns out that they have very different properties as far as evolution. So for one, you can give a simple algorithm, which evolves it at least for the uniform distribution. But for the parity function, you can show that no way. So in a fairly robust way, that's not going to happen. And just to say what it is, so for those of you who don't live on parity functions, so counting the number of zeros of ones in the sequence, that's not too hard. What's hard, and what is hard for evolution to discover by any Darwinian process, is to discover a subset on which the parity is somehow important. Okay, so it may be that if you take the second and the penultimate bit, and if an odd number of those, if exactly one of the ones is 1 and not both or neither, so it may be that this condition is really good for you. Okay, if you jump up, whenever that happens, that may be very good for you. But what evolution needs to discover, which is the important subset. So maybe these two, maybe some other subset. And so one can show that any Darwinian process cannot discover this. Okay. Which kind of says that you won't find this parity function in biology, which in fact is the case, so just as well. But mathematically, a parity function is just as simple as linear function, Boolean disjunction. So So just to finish, so the reason why machine learning and evolution are, I think, such perfect parallels is because in both of them you have mechanisms which you shouldn't think of as modeling the world. A machine learning algorithm doesn't model German or Japanese, it somehow copes with it. These algorithms don't understand what they're doing. They don't try, again, same thing, they're not modeling anything. And also machine learning algorithms do have a theory, and some of it is kind of fairly sharp. So for example, half spaces like the perceptron are learnable in a very strong way. And if you go away from it, if you want the intersection of two half spaces, then that becomes very difficult. So there's some very sharp boundaries which both theory and experience verify. And so the issues which some of the other speakers will explore are the following. So certainly the pragmatic question is, can we derive a plausible picture of what this protein expression level evolution is and does? So we just want a plausible picture which is quantitatively reasonable, can be naive. So what's going on? So the fact that we don't really understand this, I think, is shown maybe by the first point, that so the question is, do mutations arise purely from some sort of noise process? Is mutation just some noise in some natural process of copying or something else? Or maybe this mutation process has evolved itself and is very clever. So you think that we know the answer to this, but I think reasonable sets of people would differ on this.
What about the possibility that the organism might be able to transform the function from its original form? So perhaps it can't recognize parity unless it knows how to do a Fourier transform. Would that be a permissible situation?
Well, but by doing parity, I want its gene to respond to concentrations in directness parity. So you're stressing a mechanism by which you you change your genome to do that.
Well, it's not impossible.
It's not impossible, but it's probably not very Darwinian. Okay. So here I have a very kind of strict Darwinian model, The alternative is general machine learning, which is very Lamarckian. Intermediate models, I think, would be interesting, although I can't think of any. I think you're suggesting that. So there may be intermediate models which reflect some more complex aspects of heredity besides just handing on DNA sequences. Okay, so I'm open to that. And then, okay, so these are various issues which come about if you explore this model. Okay, so I've run out of time.
So I understand what you mean by fitness for a single genome, but when you talk about distribution, fitness is an expectation over distribution. I'm not sure I follow what you mean exactly by that, because don't you need some more structure about the function to be able to understand how the distribution works, or how an individual acts in order to improve the distribution? I don't quite, the expectation, I mean?
Well, I think all that happens in this model of Darwinian evolution is that you produce a limited number of variants, and you want some evolutionary algorithm works, a class works, if there's some guarantee that some of the variants you produce will have a high expectation, will have high performance. Okay, so it's a learning algorithm which you try to prove works. You hope to prove it works in all distributions. Some only work in some distributions. But that's what you have to show, that the algorithm works even if no one understands anything about it. No one knows what the distribution is, no one knows what the ideal function is. All you know is that there's some class of functions which your protein expression levels obey, but there have to be. And if it's simple enough, then it works. So we've got all the questions at some point, but okay.
So then the idea here is to find a complex enough class of functions and to show that evolution can solve that efficiently. And
Yes. It's a very parallel game to what people do in machine learning. Yes.
Hi everybody, my name is Vitaly Feldman. I'll be talking about the power and the limitations of the model, which was sort of outlined by Les. I'll also have to define it a little bit more formally. So what at the end of the previous talk, we sort of, its goal was to convince you that you could view what's evolution as a sort of restricted form of learning from examples. In other words, the classes of functions, or this sort of the classes of ideal functions that can be evolved to, are some sort of subset of all the classes that we can learn by looking at random examples. And we have seen one example. We know that this is in some sense, a strict subset. We know that, for example, parity functions are not evolvable, even though they are learnable from examples. So the goal of this talk is try to sort of at least refine this picture and try to understand what's exactly in this set and how it relates to the set of all the functions which are learnable. And here I'll be looking at this sort of completely least restricted model evolvability, where we basically allow the mutation algorithms to be any Turing algorithm which can be performed by a Turing machine. And the only limitation is that we will be the process will be this Darwinian process, where we have some mutations and some selection mechanism selects the most fit ones from those mutations. So, of course, my basic approach will be to try to relate this what's evolvable to other classes which have two other types of learning algorithms which have been studied in the literature, and of course to try to leverage what we know about machine learning to better, hopefully, better understand at least the model, and eventually, of course, we hope that it will help us shed light on evolution as it occurred on Earth. So to make the discussion more concrete, I'll have to go into some definition. I'll have to actually define what do we mean by learnable from examples, and my focus will be on learning of Boolean functions for several reasons. First of all, this is how it was initially defined, and also we have a more sort of detailed theory of learning of Boolean functions than we do for real-valued functions. So let's start with the core model of learning, which is referred to as probably approximately correct learning, PAC model, which was defined by Les Valiant 30 years ago and has been studied really extensively since then. In this model, a learner is thought of as having access to some random examples, which are pairs in which x is some point, and f of x is a value of some function on that point. And in this case, we'll be looking at Boolean functions. This point x is drawn randomly from some distribution d over our domain. And domain is, again, if you like to think about these proteins, these are expression levels of proteins. We'll think of it as abstractly as either, say, real-valued n-dimensional space or Boolean n-dimensional space. It's depending on the type of functions we'll be interested in. And we'll assume that this unknown function, which labels those examples, comes from some known class of functions. So it is not completely unrestricted. It is unknown, but it's restricted to belong to a certain class of functions, which will denote by C. And the goal of the learning algorithm is for every function from that class, and every error parameter will have to, I mean, you can think of it as just, say, fixed value of, say, 1%, but in general, these learning algorithms are usually parameterized by the desired error. With high probability, the goal of the learning algorithm is to output a hypothesis function h, which we'll think of as taking values between -1 and 1, which has low error, which is very close to this unknown function. And the notion of closeness is one way to think of it as we want this sort of expectation of the product between these two functions to be very close to 1. And of course, this is a ±1 function. This is one way to think of it as if h, for example, the hypothesis was a Boolean function. This means that these two functions agree on all but the very small fraction of the inputs. Yes?
You defined with high probability.
I will have to skip some of the details, but you can think of it as negligible, so very close to 1 for all practical purposes. Let's put it this way. This means that we can. It actually doesn't, in learning context, it doesn't even matter because it's very easy to amplify the probability of success. So you can make it by just repeating your learning algorithm. You can make sure, and testing the hypothesis, you can always achieve any probability. But I'll necessarily have to swipe some of the more technical details under the rug to keep at least some of the intuition reasonably clear. But of course, if something doesn't make sense to you, please ask. And any more questions? Yes?
In the biological setting, doesn't one have to worry about hidden variables that are not observable to the learning function?
So we'll get to biological. You would be saying that the sort of unknown function is not fully determined is not always determined by, is not always 1 or -1. It could have, because of some additional factors, it's not fully predictable. Certainly, both in learning and in biology, there is this potential element that's sort of, and there are different ways to model it, and many of them can be transplanted from learning to biology. I will not, for simplicity, I won't be talking about these sort of more complicated, more involved models. And of course, we want the learning algorithms to be efficient, by which we'll mean that they run in time polynomial in the dimension of the problem, and the inverse of the accuracy. Again, this might it's not as important. You can think of it as just a fixed small constant. So I haven't said what is the distribution relative to which we measure. Ideally, we want learning algorithms which can achieve this goal for any distribution, for examples which come from any distribution D over the domain. But sometimes we'll be happy with algorithms which succeed for some restricted distributions which are sort of fixed and known to the learning algorithm. So this is, we're still looking at learning. And again, I can go back to this classical example of a function class of half spaces, which are just, or also referred to as linear threshold functions or perceptrons. And these are functions which can be expressed as a linear threshold function, some weighted combinations of the attributes, sign of the weighted combination of the attributes minus some threshold. And the assumption that that examples that we see are labeled by such a function is equivalent to saying that the examples that we see with positive and negative are linearly separable by some hyperplane. And of course, there are many different algorithms to learn this class, but the simplest one and the oldest one is the Perceptron algorithm, which Les already mentioned, in which we maintain some hyperplane, and we look at each of the examples that we have, and whenever we see an example which agrees with our current hypothesis, we don't do anything. If we see a counterexample, then if that counterexample is positive, then we add the example itself to the weights, to the current weights. Otherwise, we subtract it. And it's known that under some mild assumptions that the examples are separable with some relatively wide margin, this will give you a packed learning algorithm. So now let me talk a little more about how one could define evolution algorithms a little more formally. So first, we'll need to define some representation class of representations, and these will be all the functions that can be represented by whatever the organisms that will be mutating. We need to make sure that we specify those explicitly and specify which function are computed by each of those representations. And for example, these representations can be some linear threshold functions, but that could be polynomials, or in general, we don't restrict them any further. It could be anything computable by a Turing machine. Then the only other thing we need to specify sort of an evolutionist algorithm is some randomized mutation algorithm, which basically the input to that mutation algorithm is the current sort of representation, or you can think of this representation as being the genotype, and it outputs it's a randomizer which outputs some mutation of that algorithm. And the only way we restrict it is we want it to be, again, efficient, polynomial, and again, inverse of the accuracy and the dimension of the problem. One simple example you could think of, if your representation, if all you represent is linear thresholds, you could mutate them by, for example, changing the values of the weights. And so far. So we need to now define how some sort of instantiate some sort of model of selection which acts on these mutation. And there are different ways to do this, and I'll stick to sort of a relatively simple and plausible way to define it. But there are other ones, and I'll discuss what these choices, how they affect the model. So first, of course, we need to define the fitness performance, which we have talked for a while. Again, it is measured as some sort of distance to this ideal function f, and in our case, it will be just the same expected correlation between this ideal function and the current and the function computed by our representation. Again, if you think of those, if those two are just Boolean, this is just the probability that they agree, essentially, up to a small shift. So now, given this fitness, the selection works as follows. First, given the current representation, we run this mutation algorithms p times. We'll choose p later. to obtain some sort of pool of mutations. And for each of those mutations, we estimate empirically what is their performance. So we look at their empirical performance, and this is empirical it's a performance on the basis of some S random observations, where each observation, S random experience, where each experience is drawn from the same distribution D, and we look at what is the correlation on these random examples. And so we estimated for each of the mutations, and let's say these are the values that for empirical performance which we get on the scale from -1 to 1, because these are functions between -1 and 1. Then, okay, one way to decide who is going to survive is to have some sort of fixed threshold T, and for all mutations whose empirical performance is by at least T larger than the empirical performance of the sort of current representation which we are now, if we have some mutations which with this higher representation, we can select one of them randomly and uniformly. We can also consider models which will just select the best one or something like this. And in case if there are no beneficial mutations, one could always the output of the selection mechanism could be defined to choose one of the neutral mutations, and the neutral mutations are all those mutations which with performance or empirical performance within this threshold T of the current representation. If there are no neutral mutation, we can assume that we are either stuck in the current representation or just go extinct, which also happens. And so these sizes of the, as Les has mentioned, the size of the pool and of a mutation and the number of examples we use to get these empirical evaluations of performance have to be feasible, which for us will mean polynomial, again in n and one of the desired accuracy. Far, so good. So, given the definition of mutation and selection, we can say that a class of function C is evolvable over some distribution D if there exists this sort of evolution algorithm which consists of representation and mutation and some polynomial number generation, such that for every ideal function from that class, and for every error epsilon, starting from this from any representation R, a process which starts at any representation R and then applies selection to R, and and selection is some sort of randomized process. This process will converge after G generations. This process will reach some representation with whose performance is very close to optimum. Again, with high probability, because it's a randomized process. Ideally, we would like to have evolution algorithm which can do it for any distribution over. So they don't need to know anything about the distribution over the experience, and they work for all. But sometimes we will be happy with those which we can work at least for some distributions. So now that we have the definition, we can discuss what more formally what can we say about evolvable. And one very simple constraint that one can notice is that the feedback to these evolution algorithms is about the unknown target function is restricted to these values of empirical performance. So basically, one sort of most obvious restriction is that that you cannot see anything but empirical evaluations of performance for some functions, which are your representations. There are other restrictions, but this is sort of the most obvious and the first one. And we can capture this restriction by defining a class of algorithms which are only restricted in this way. They can do everything else. Other than that, they can be any learning algorithms, but they have to. But the only extent that they have to the target function is through this empirical performance. And the way to formally define it is to have a learning algorithm which has access to some oracle and can ask for any function for any function can send us some sort of hypothesis function to the oracle, and the oracle will respond with some value v, which is exactly the sort of empirical performance of this hypothesis, evaluated on some S fresh experience or examples, whichever way. And then, of course, learning algorithm can ask for another, for performance of another function, and so on and so on. And at the end, it needs to output a hypothesis. And the point is here that it's just a general learning algorithm with a restricted view of the unknown function. So having access to this oracle basically allows us to simulate any evolution algorithm. And this means that what's evolvable is a subset of what can be learned by the algorithms of this type. So one way to draw it would be, okay, we have this picture that this is all back learnable from example. We know that evolvable is somewhere here, and this is what's learnable with this oracle. However, it turns out that this sort of restriction on the algorithm that I have just defined has already been studied in learning theory. And one way to describe it is studied as learning by CSQs of correlational statistical queries. It was definition is slightly different from what I did. Instead of it's learning with an oracle, which instead of giving the sort of empirical performance, it gives the value of the performance up to some tolerance tau. So it commits to some value which is close. It responds with some value which is close to the empirical performance, but it's not necessarily computed from random fresh examples, but it has some. It's very close. You can control how close it is to the true value. This model was first defined in 90s by Ben David and Kushlevich, and it's also related to the statistical query model I'll describe later. It's a restricted version of it. So,
Can you just elaborate? I mean, so for something biological, you're always given a fixed, limited number of genomes to select from after your mutation process. So the biological thing is empirical performance?
What do you mean you have an unlimited? So unlimited is that, yes, mutation algorithm can, in principle, produce unlimited number of mutations.
In biology, you're stuck, you're restricted to a limited...
Yes. This is the first step, that there is a limited number of, the limited pool of mutations that you can select from is limited. If you remember, there were two steps. First, you sample some number of mutations. This is your pool of mutations. It has to be limited, and for that pool of mutation, you estimate the performance of each of them by only looking at a limited number of evaluations or experience.
Is it essential to the proofs that your selection, that you are allowed to take an arbitrary number of examples and then only then you get epsilon convergence, or can you say that you're going to do selection after taking 10 examples, sample genomes, and just keep...
Well, for every specific value, that for every specific value of epsilon, which would be how close you are to the target, you would get some specific value of generations and population sizes that would suffice. But we are interested in sort of understanding of how these populations scale with the closeness with the error parameter. Okay, let me.
You're giving a lower bound on tau there.
Mm-hmm, yes.
Don't you want to sort of bound it from above?
I know. This says that the oracle cannot be. You can ask for this value up to a certain tolerance, and you cannot ask for tolerance which is too small. So because otherwise you won't be able to estimate it from random examples. So given that these algorithms are not restricted to be Darwinian, they only restricted to look at performance model. We expect that this is a much smaller set evolvable than this, but it turns out that actually they are the same, and that's perhaps a little bit surprising that actually everything which can be learned, given access to this this correlational statistical queries or performance oracle can also be evolved. And let me briefly sketch on how one would prove this. So the first step, so in order to prove this, one would need to simulate these sort of queries to the oracle, which ask for values or approximate values of the performance using an evolution algorithm. And the first step will first simplify our queries. Instead of asking for values, we'll only ask for comparisons of the value with some threshold. So we'll basically reduce. So we'll first say that it's in order to simulate the algorithm which has these queries for value, it's sufficient to actually simulate an algorithm which only performs these comparisons. And the reason for this, and these are sort of, let me just specify this, what are these approximate comparisons. These are comparisons which for every hypothesis h and some tolerance parameter tau and threshold t will return 1 if the performance is greater than threshold plus the tolerance. They'll necessarily return 0 if the performance is less than threshold t minus the tolerance, and if it's very close to the threshold, they can return anything they want. And the reason one can reduce to such a comparison is just very simple. If you can just do some sort of approximate binary search and get from this comparison, you can derive the value itself approximately. So the next and more interesting step is how to design evolution algorithm using mutations which allow one to simulate such a comparison. So to get answers to these comparisons using some algorithm which actually is sort of an evolution algorithm. So again, our goal would be simulate such a comparison. And to give you an indication why this would be possible is let's think of the following mutation. Let's assume that we have some representation which computes just a pure 0 function, which is always 0, and its performance is obviously also 0. And it has just two mutations with very high probability. It outputs the same 0. It just doesn't change. It's a neutral, completely neutral mutation. And with small probability, it outputs the representation which computes the hypothesis function, for which we are interested in, and we are interested in understanding whether the performance of this function is greater than some threshold t or smaller, approximately. So we can choose. So if we assume that the threshold between beneficial and neutral mutations is exactly t, which is then by choosing relatively small mutation pool size, it just depends on this delta, and relatively small performance size. What we can see is that if the performance of this hypothesis h is greater than the threshold plus this tolerance parameter, then its empirical performance will be greater than the threshold, because it will be estimated within tau given the large enough sample size. And what this will mean is that this representation will be considered beneficial, and as a result, it will be output. So in the next sort of generation, we'll have this representation. If this hypothesis h, its performance is less than t minus threshold minus the tolerance, then the empirical estimate will be less than the threshold, so it will be considered neutral. And since both of these mutations are neutral, but this is much more frequent, we'll know that this will be a much more likely outcome of the mutation, of the selection procedure. So what we can say that with high probability, the output of selection will be some representation RB, where B, this index B, is a valid response to this comparison query. So a mutation, it's sort of the outcome of one mutation in the next generation actually gives you the answer to a comparison query. And this allows you to implement, and this at a high level allows you to implement algorithms. I won't go into further detail, but basically you can extend it to answering more than one query just by sort of composing and rescaling queries. I don't quite have enough time for this. And once you know the answer to these queries, you can compute since your algorithm can just compute you have a learning algorithm which can compute a good hypothesis. Once you have that hypothesis, you can mutate into this hypothesis and have a hypothesis which has very high performance. Again, we're talking here about things which can, in principle, be done by evolutionary algorithms. So again, going back to this picture, another advantage of this equivalence is that actually easy to show that it's robust to many modeling choices of evolution. So, for example, it's easy to see that one cannot really increase the power of what's evolvable without changing the fitness function that we look at, simply because everything which just looks at this given fitness function will obviously include it in this CSQ learnable. And that implies that, for example, even if we have a selection mechanism which does sort of more complicated optimization, or even if we allow some form of populations with recombination, we'll still be within the same set of evolvable classes of functions. And other things, and one can also look at more restricted models, and it's easy to show that you can still achieve the same result. Even, for example, if you only allow one non-neutral mutation, you can still get all which is CSQ learnable. Okay. So the question is now, how powerful is the CSQ learning? What can you do? And to understand it, it's useful to understand another model, which is SQ learning. So just a more general oracle, which allows one to, for every function which depends on an example, allows you to get an expectation of that function of an example within some tolerance parameter tau. And you can see that previously we had a special case. We were only allowed to look at correlations, and this is any function of an example. This model has been introduced in '93 and studied quite extensively. We know that pretty much everything we can do in machine learning can be done using such algorithms. It doesn't matter, so certainly Boolean conjunctions, linear threshold functions, general machine learning techniques can all be implemented using statistical queries. One thing we know that we cannot do is parities, and this is that's the reason why we cannot evolve them. And what's the relationship of this? So this is a very powerful model, almost essentially as powerful as what we can learn from examples. And to give you a little bit of an intuition why it's true, we can look at how one could implement this Perceptron algorithm, which is really relies strongly on examples using statistical query algorithms. And to implement it using statistical queries, one simple observation is that in order to perform these updates, which we need to do on counterexample, let's assume that this is our hypothesis, or the true one. Instead of we don't really need the examples themselves. It's sufficient to know the centroid of this region. And the centroid of this region already is some sort of function of a distribution and rather of individual examples. So it's easy to estimate using these statistical queries. We can just estimate it by coordinate, and then obtain some point which can be used to perform the update of our hypothesis, and we'll still get the same convergence guarantees. So the reason why we were interested in learning with statistical query model is that if you fix the distribution, then actually statistical queries is as our model of correlation statistical queries is as strong as learning with statistical queries. And the proof is very simple. Okay, it looks like there's maybe a few formulas, but actually extremely simple expression proves that you can decompose a general statistical query into two queries, one which is for a correlation that and the other is one it does not depend on the distribution, and therefore if you know the distribution, you only need to ask for correlations.
Isn't the distribution typically fixed?
No, in general, well, it's fixed it's fixed, but it's usually not known to the algorithm, to the learning algorithm. And here, to be able to simulate, you need to know the distribution, that it's some specific distribution. to be able to know what are these sort of distribution-specific constants. Okay, so one simple corollary is that if we know the distribution, if the distribution is fixed, then we can evolve even this important class of linear threshold functions for any fixed distribution D. So for distribution-independent learning, things are actually quite a bit more complicated. We know the only example that we know that things which are evolvable without knowing anything about distribution are functions for which only very few points are positive. So they're, say, negative everywhere and positive in just, like, say, 1 or 5 points. Or the other way around could be negative everywhere and positive in one place. We know that weak learning, without assumptions on the distribution, can be characterized as follows. So first of all, weak learning is learning where your hypothesis needs to be just a little bit better than random guessing. Its correlation with the target needs to be slightly better than some small fraction. And we know that in order to even weakly learn, the functions in your class need to be representable as linear threshold functions with significant margin over some small basis of functions. So they have to be in some space. They have to be some space of small space of features. They have to be basically linear threshold functions, and we know with significant margin. And this means that we can now use some results from communication complexity to show that general linear thresholds, those which do not have a margin, will not be learnable distribution independently, even weakly. And unfortunately, for strong learning, even simpler classes we know will not be evolvable distribution independently. Even simple conjunctions are not evolvable. Let me conclude this picture by saying what are some of the sort of more technical questions that one would like to understand to better understand the power of evolvability. It would be nice to understand better what is the strong, how one can characterize the strong evolvability in this model, and maybe one can in particular strengthen the lower bound for conjunctions. Right now there is a lower bound, but it's relatively, we cannot match it with an upper bound. One natural class for which we don't know whether it's evolvable distribution independently is the class of linear thresholds, just a one-dimensional linear thresholds. Very simple natural class. We don't know if it's evolvable distribution independently. And finally, we can also go beyond this sort of fitness that we have looked before. Instead of looking at the fitness defined by the correlation, we can look at this fitness defined by the quadratic laws, that another relatively natural way to measure the closeness to the ideal function. And interestingly, for this notion of fitness, one can evolve, in principle, everything which is learnable by statistical queries, which we know is a very big and essentially as powerful as what we know about learning from examples. And we know that machine learning is quite successful at what it does.
So that's for arbitrary distributions?
This will be even for arbitrary distributions. Anyway, that's the end of the talk. Sorry for running a little over.
Your definition of evolvability is different from the definition of evolvability where you actually learn an exploration distribution. So learning which samples are going to generate high mutation and changing the mutation. Do that.
Yeah, I think yes.
This doesn't include how evolution can learn the structure of its exploration.
Yes. Yeah, I'm around if you have a question. I understand probably a little more technical than some other talks. Thank you again.
Okay, so my name is Varun, and I'm going to talk about evolution of a simple class of functions, in this case, linear functions, and I'll try to motivate some of this work a bit more by sort of looking at biological systems, and this is joint work with Elaine and Angelino, who will talk next. Okay. So let me very quickly summarize the previous talk. So in the first model, sort of Les Valiant introduced sort of a framework to try and understand the question of how complexity arises in evolution. And sort of the idea is there's a genotype, which is a string representation, but this also encodes some function, which is the phenotype of the organism, which is some function from x to y. And this x can be some x1 to xn, which is the concentrations of various proteins in the cell, which represents the environment for the organism, and y is some desired output, which could be expression level of a particular protein. And there's an ideal function that sort of describes the best behavior in every possible setting. And what we want to try and understand is for what classes of ideal functions is evolution feasible. Okay. Okay, and if we look at sort of in a picture inside a cell, what we have is these sort of lots of sensors, which are just some kinds of proteins, which are called transcription factors. And these represent what the environment around the cell is as far as the cell is concerned. Okay, so that's the picture the cell gets about the environment. And these factors affect the production of genes through interactions with the DNA. So by physically binding and repressing or activating a production of protein. And that's how they control how much protein is produced or whether or not it is produced and so on. And in the last talk, Vitaly showed that there's a powerful class of learning algorithms. There's a particular kind of statistical query learning algorithms, which, if you have these algorithms for a class of functions, you can cast them as evolutionary mechanisms in the framework that Les Valiant introduced. And so this shows that in principle, at least, evolution is very, very powerful. And the mechanisms that he talked about indeed fit in this framework. But what I'll focus on this time is the representations that they actually use. And the representations used might be quite complex in the actual evolutionary mechanism that comes from converting these learning algorithms into evolutionary mechanisms. Okay. So in this talk, I'm going to try and focus on representing functions. So here's my attempt at drawing a complicated circuit. So in Valiant's model, so representation is just a string, but this encodes a function from some space to y. And in general, this function is allowed to be sort of an arbitrary circuit that can be polynomial in the number of input parameters. The size of the circuit can be quite large. And if we look at some biological circuits, so let's look at how gene expression actually happens. So DNA is where the actual protein is defined. The sequence encodes the sequence of amino acids in some way. And the DNA will be transcribed into a messenger RNA, which is then eventually made into protein. And the way the production is controlled is there's a particular molecule called RNA polymerase, which sort of binds physically to the DNA where the gene is defined, and it starts copying it to make an mRNA. And how easily this RNA polymerase can bind to the DNA is affected by many factors, so some of these are called transcription factors, which sort of physically bind to the DNA just upstream of where the gene is defined. And they can either sort of enhance or repress how easily RNA polymerase can bind to produce the particular protein. Okay, so this is how circuits look like in biology. And so if we think of what these representations are, and let's, in particular for prokaryotes, which have quite simple sort of gene expression networks, what's observed is that the degree of the networks, which is sort of the number of transcription factors that affect the production of a single gene, is actually quite small, so maybe somewhere between 1 and 10, or 1 and 12. And the depth of the network, okay, so this is basically comes from the fact that the promoter region is only maybe like 200 base pairs or 300 base pairs. Okay, so there's not many transcription factors can control the production of a single gene. And the depth of the network is also quite small, so maybe 1 through 4 or something like this. And again, the reason for this is somewhat physical, because it takes time to produce protein. And if the protein needs to be used for something, you need to produce it rather quickly. So you don't want to wait for a long sequence of events to happen before the protein is produced. So in general, for sort of bacterial cells or something, the cell division time is the same order of magnitude as sort of time it takes to produce protein in sufficient quantity. Okay. So if you look at this circuit from sort of a computer science perspective, what you would say is that this is a circuit that has small depth and small fan-in. Okay. But if it has small depth and small fan-in, then it automatically follows that the output should depend only on a small number of variables. And so essentially, this might be just a junta, so there might be a large number of variables, but the output for any single expression depends only on a small number of them. Okay. And so we want to try and understand.
So I guess why does that follow that it only depends on a small number?
So if you have, let's say if you have depth 2 and fan-in 2, so you can only have say 4 variables that affect the output, right, in the circuit.
Number to the power of a small number can be a big number.
Sorry?
If the depth of the circuit is small and the fan-in is small, right? So you're saying that the number of input variables that it can be dependent on is a small number to the power of a small number.
Yeah. Okay, so that's okay. So actual numbers, okay. So maybe so 10 to the 10 is a large number, but so 4 to the 4 is not. So maybe that's even large. Okay, so unless that. Okay, so in sort of in the world of computer science, I would say that both of these are constant, so the input depends on constant number of circuits, of inputs. Okay. The output depends on constant number of inputs. Okay, so and so I'm going to talk about sort of an evolutionary mechanism for a particular simple kind of sparse function, so which is a sparse linear function. So let's say that the ideal function, which is defined by these concentrations of as a function of the concentrations of various molecules, so this n could be fairly large, but the ideal function is actually quite sparse. So it depends only maybe on 4 or 5 or 10 of these. And it's a linear function, so these xi's are all real valued, and f is also the output is also a single real value, real number, and the performance is going to be defined by using a squared loss. Right, so ideal function is f, the organism computes some function r, and the performance of this is just the negative of the expected squared loss. Okay. And I'm going to describe an evolutionary mechanism which has the following nice property. So the representation that's used during the evolutionary process is going to be a sparse linear function at all times. So the sparse linear functions sort of can be represented as a depth 1 arithmetic circuit with weights on the edges. Okay. Okay, and sort of before I describe the evolutionary algorithm, just to connect this to sort of more classical machine learning, so this is really just a problem of sparse linear regression, trying to learn sparse linear functions, and of course this has been studied a lot in various different fields. So the general problem of finding this sparse solution to an underdetermined system of linear equations is NP-complete. So you don't expect an evolutionary algorithm to succeed, and in fact no algorithm to succeed in this problem. But if we make some assumptions on the distribution over the inputs, then this hardness assumption is sort of broken, and this is what I'll talk about. Okay, so we describe the setting in a bit more detail. So the functions that we are going to consider are going to be linear functions, and I'll represent them just by some vectors, so w, and where it takes x to w dot x, and the sparsity of w is going to be at most k, and I'll further also make the assumption that each wi, which is either 0 or it's bounded both below and above. So none of the wi's is too small, otherwise it's 0, and none of them are too large. And I'm going to talk about a class of smooth distributions. So what's a smooth distribution? So let me define what I mean by a smooth distribution, and then I'll show a picture in the next slide. So so let d twiddle, let's say, be a completely arbitrary distribution over Rn as long as it has bounded support. So it's the support is in some bounded ball in Rn, let's say, and you draw some x twiddle from d twiddle, and now for each element of x is a vector valued for each I, xi is going to be defined as xi twiddle plus eta I, where eta I is some uniformly chosen number between minus delta and delta. Okay, so it's some random noise in each xi. And now the distribution that we actually care about is the distribution over x, which is in some sense smooth because of the noise that's been added to this. Okay, and I'll assume that this the expectation of xi square is bounded. That's can be managed by rescaling. And so sort of pictorially, so these distributions is inspired by the work of Daniel Spielman and Shenghua Teng on analysis of the simplex algorithm. And so essentially what we're doing is maybe the starting distribution was completely arbitrary and complicated like this, but if you add some noise to every measurement, which is sort of equivalent to convolving it with some uniform distribution, and what you get is a distribution that looks like a smooth distribution. Okay.
So smoothing the function itself.
Smoothing the function. So right now we're looking at linear functions with sort of bounded coefficients. So the function itself is already very smooth. So, is that what?
There's a formal way to define using noise operations.
I see, and I see. By looking at small, yeah, I see, yeah. So that's not something we've looked at, but that's. Okay, and now let me just say what representations I'm going to use in this evolutionary algorithm. So the representations themselves will also be sparse linear functions. Again, I'll denote them by a vector W. But the sparsity of W can be slightly higher than the sparsity of the ideal function. So the ideal function had little k as its sparsity, and it'll allow some big K. And each of the weights in this Wi can also be bounded by some b. And both k and b here will depend on sort of k, which is the sparsity of the ideal function, u and l, which were bounds on the weights of the ideal function, and delta, which was the noise. But they don't depend on n, which is the total number of parameters. And we quickly fix some notation. So this representation which is r of x, let's say, is just some linear function. And so nz of w, this will denote the set of all non-zero entries of w. And I'll define the inner product on vectors as the expectation of this quantity. So I look at w and w prime as both linear functions, and the correlation of those linear functions is their inner product, and the norm is defined similarly. So I look at the squared error of the functions represented by w and w prime. So this is the notation I'll use in the rest of the talk. And I want to please skip this. If I can do the proof, then I'll come back to this. So let me define what the mutation algorithm is. So the current representation is just some sparse linear function. So it's some sum over I wi xi. And basically, there's going to be very simple mutations. So there's two types of mutations. So the first is what I call sort of adjustment mutations. The first one is sort of just randomly rescales the current representation by some alpha n minus 1, 1. And this is, I don't even think this is really required. This is just for some convenience in the analysis to ensure that this doesn't get unbounded. The second one, which is changing the value of a single coordinate. So my current representation is w, and I update it by sort of removing the ith element and adding a completely random value in its place with the ith element. So I'm taking a particular coordinate and just setting it to a completely random value. So that's one kind of mutation. And so these are just sort of not changing the set of variables that I have in my representation, but just fiddling with the coordinates on them. Okay. And the second type of mutations are ones where I'm actually going to change the set of variables in my representation. So one would be to add a completely new coordinate with a random coefficient. And this may not always be possible because I want to ensure that the representations I'm using are also sparse. So in that case, I'll use a different mutation, which is randomly adding and deleting a coordinate, so just swapping out a coordinate. Okay, so this is, and so the mutation algorithm is defined as doing one of these things at random. So, and you'll get a pool of mutations that can be obtained by running the same algorithm over and over again. So you'll get a reasonably large pool of mutations. And what I want to show now is that as long as you're far from the ideal function, you'll always make progress by some mutation of this kind.
The distributions of like how big, how much you're resetting them by, that's going to change with time, or that's staying the same?
No, so it doesn't. So it's completely arbitrary. It's fixed. But I'm going to consider lots of mutations. So I'll show that with reasonable probability, I'll get a value of beta that's useful.
Now the notations are on W, but the smoothness is on the X's, correct?
On the X's, yes. Okay, and so the proof that this works is a bit, it's not hard, it's just a little bit of calculation. So the first one is to show that sort of, if I don't change the set of variables that I'm working with, so let S be non-zero variables in W, and so of course, maybe W is already the best possible representation of the ideal function using this set of variables, but if it's not, so let's say that the best possible representation of the ideal function using this set S is Fs, and my W is somewhere here, then that means that this residual, this green vector is somewhat large. And what that means is that there must be some vector within, or some variable within the set S, which is correlated with this residual vector. Okay, and how exactly these, to show that this is actually a significant correlation, you need to use the property that the distribution is smooth. Otherwise, this is not true. But as long as the distribution is smooth enough, then this is true that you get a non-trivial improvement just by changing the value of one of these variables. Okay. And the second half is that if you're not, so now maybe W is, if I don't change the set of variables, W is more or less the best that you can do in this current set of variables, but if you're still far from F, that means there's a significant component of F outside of the span that you get by using variables in S. And again, this means that there's some variable that's in F, which is not in your set S, which will have a significant correlation with this. So the analysis is not hard, it's just sort of chasing these quantities correctly and using the smoothness of the distribution to ensure that they're actually non-trivial improvements. Okay.
Some variable from S can be discarded by its low influence, but am I misunderstanding? Some of the variables have no influence. Is that what they do because?
So they may because I'm not assuming that the distribution the variables are independent in any way. So some of the variables in S, although they're not in F, they might be correlated with the other variables that are in F. So the current representation might be trying to use them to get close to F. But the point is, at least one of them will have less influence than one of the variables that's actually in F. So what I'm saying is that there is some variable in true F which is missing from S, which will have more influence than some variable that was not in F but was in S that W was using currently.
So what if this new variable is one of a million? So there are a million variables. So this new influential variable is one out of a million, and you need to find it.
Yeah, so the number of mutations does depend on the total number of variables. So if there's a large number of variables, then the population that you need is large, but the representation that is used is still sparse. So
can't you put more restrictions on where to find the influential variable?
So that's the question. How does evolution know which variable is important? And it's going to just do it by some mutation. And if your space of variables that you need to look for is large, then you have no option but to have a large number of mutations. Okay, so here's an informal version of the theorem. So what this says is this very simple mutation algorithm that I described on the last slide, a couple of slides, does indeed work in evolving the class of linear functions, sparse linear functions. And furthermore, it has these attribute efficient properties where sort of all the representations in the interim are also sparse linear functions, and the number of generations required also depends only on the sparsity of the ideal function and the accuracy, but doesn't depend on the total number of variables. Okay. But the population size, so the number of mutations you need to explore, which is related to the population size, does depend on the total number of variables.
The number you need to explore to find one which is beneficial.
Yes, that depends on the total number of variables. Okay, so we just sort of summarize this talk. So what we're trying to look at in this talk is sort of look at the particular constraint that biology imposes on how we represent some functions, and see how the language of computational learning theory can be used to frame these as constraints on the resources that a learning algorithm, evolutionary algorithm, is allowed to have. And one natural question is, if you look at other biological systems, you might get different constraints. And can you perform similar analysis by imposing different kinds of constraints on the evolutionary algorithm? And also, a different direction is, what are other classes of sparse functions that you can evolve? So maybe not just linear functions, but low-degree polynomials, or even linear functions composed with nonlinear filters, which seem to appear a lot in sort of biology. And sort of the most interesting question, which Elaine will talk about now, is we want to try and understand what functions do gene level expression levels actually represent. So if you look at the expression level as function of concentrations of transcription factors, what are the functional forms of some of these expression networks, and can we understand them? And so that's what Elaine will talk about, so I'll stop right now.
There you go. It's showing something.
Yeah, it's not enough.
That's pretty cool.
Okay. So I think this question has been quite well motivated at this point. If we're going to be serious about studying evolvability, then it's probably time that we learn a little bit of biology, or a little bit more than we've seen so far. Varun just spoke about some of our previous work to study the evolvability of sparse linear functions, where this choice of function class was basically inspired by things that we see in biology. And now our current goals are to insert some more biology into this evolvability framework. And so this requires identifying a coherent framework for describing things that we see about gene expression and transcription. And an important point that I want to make very clear is that I will not be talking about any of my own work today. I will only be talking about things that we've learned recently by reading other people's work. So you'll see a bunch of references, and most of the figures and examples are not actually my own. And the purpose of this outline is to basically say that there should hopefully be something here for everyone. We're going to start by learning, by reviewing some basic biology, and then we'll write down a mathematical model and try to study the solutions that pop out of it. Varun already went over these basics for you. Just as a reminder, we'll be focusing on transcription, which is the process of reading the DNA and producing mRNA from it. So for the purposes of this talk, gene expression level is going to be proportional to the amount of time that, or rather the fraction of promoters in the cell that are bound by the RNA polymerase molecule that is required for transcription. And what we'll see in this talk is that the promoter can exist in many different states, potentially many, or multiple, and in general, this polymerase molecule can only bind to some of these states. Okay? So we better start simply with where we think of the promoter as a two-state system. So here we have a promoter, and on the left it can either be empty, or on the right it can be bound by a polymerase molecule. And so this allows us to think of the system as a Markov chain with just two states, and then there's rate constants that describe the transitions between these two states. And if we think of the probability of being in either one of the states, what I've said before is that gene expression is the gene expression level is going to be proportional to the probability of being in the state where the polymerase can bind to the promoter, the state on the right. Okay, so here we have, we're going to suppose that there are P of these polymerase molecules, and the DNA has one special promoter site that we're interested in, and we're going to think of the rest of the DNA as uninteresting, full of N non-specific sites where this polymerase can bind. And what we need to know is that in general, the energy of the polymerase being bound to a non-specific site is in general different from when the polymerase is bound to the special site of interest, the promoter. And there's going to be some difference in energies. And one thing that you need to know is that the probability of being in a state is proportional to the exponential of minus the energy of that state. Okay, so now we can write down the partition function of this system. The term on the left, oops. The term on the left is for describes the state where P of the polymerases are bound to the DNA at non-specific sites, and then all we're doing here is we're counting the number of arrangements of the molecules, of the P molecules at the N-specific sites, non-specific sites. And then on the right, we have something analogous, but where P minus 1 of the polymerase molecules are bound to non-specific sites, and then the one polymerase is bound to the promoter. And this okay, so let's just give these two terms names, X and Y. Now we can immediately write down the probability of the polymerase being bound to the promoter. It's just the probability of being on this side, Y over X plus Y. It's convenient to rewrite this as 1 over 1 plus X over Y. We do a little bit of algebra, plugging in all these expressions, and also do a little approximation for a large N limit, and we get this. So 1 over 1 plus N over P times an expression that depends on the energy difference between the two states. And we can go a little bit further invoke Arrhenius and relate this energy difference to the ratios of the rates that have to do with the binding of the polymerase to the DNA. And then this P over N we can think of as the concentration of polymerase. Okay? So what we have here is that gene expression in this very simple system is a function, a simple function of the concentrations of molecules in the system and rates of binding. So now we're ready to look at maybe a more realistic promoter system. So here we have a promoter that can exist in 12 different states. I'm going to tell you that gene expression is allowed to happen in the states on the right. And the main point to take away here is that this is described as this graph, right? So we have states and transitions between the states. And so now we're going to break down the graph a little bit so that we can understand what's going on. Pardon?
How many transcription factors were there in that picture?
So there's two sites where transcription factor can bind. So that's what I'm showing here. So we think with the promoter, this promoter in particular has 3 regions. And these regions can either be occupied or unoccupied. In the first region, we can have a transcription factor bind. In the second region, a transcription factor or a nucleosome. And in the third region, we can have a nucleosome there. And what's happening is that that the nucleosome gets in the way of the polymerase at the third region, and then there's no, and so we need this third site to be free to have gene expression. Okay? This happens in half of the states. So let's take a look at these transitions. In this particular one, it's one of the horizontal transitions, we have a nucleosome being removed from or added to this third region of the promoter. And what you need to know is that these forward and backward rates are physical constants of the system. However, there's some other transitions that depend on transcription factor being around. And this is a protein, right? This is a protein that's floating around in the system. And so the adding of a transcription factor corresponds to a binding reaction. For the physical regime that we're interested in, we think of the rate of binding as proportional to the amount of free transcription factor. And so this is relying on a standard assumption for this system that the amount of free transcription factor is approximately constant with respect to the timescales that we're interested in here. Okay, so now we can look at this picture and sort of have a better feeling for what's going on. The other things I want you to notice about this graph is that it's relatively sparse because the restrictions on the kinds of transitions between states that are allowed. And it is strongly connected, meaning that you can get from any state to any other state along a directed path. And an interesting thing to notice is that some of the transitions are not reversible. Okay? So now we've motivated a graph-based framework where the vertices correspond to states of the promoter, and the edges are directed and labeled by these transition rates, so they're non-negative numbers. This describes a continuous time Markov chain. So let's say xi is the probability of being in state I. Then we can write down a dynamical system, a linear dynamical system, to describe the rate at which these state probabilities change. Okay. We can also write this as a matrix multiplication, where some of you may recognize this matrix as the Laplacian of the graph. An important property of this matrix is that its columns sum to 0. And we also have a conservation of mass, right, because these xi's are probabilities. And so now we're going to focus on just strongly connected graphs. This is a physically meaningful setting, as we saw from the earlier real biological example. And an important feature is also that these results in this setting can be generalized to graphs that are not strongly connected. And a useful way of thinking of strongly connected graphs that we'll come back to later is that you can think of them as having at least one spanning tree rooted at each vertex. So I'll explain what that means. So a tree is a graph with no cycles. A tree is spanning if it has all the vertices of the graph. And so there are going to be one fewer edges than the number of vertices in such a tree. And to be rooted at a vertex means that all paths lead to that vertex. Okay, so this spanning tree is rooted at vertex 1. This graph has 2 spanning trees rooted at vertex 2. And let's just, for fun, enumerate all the spanning trees of the graph. Okay. So now what we're going to do is throw dynamics out the window and solve for steady state for these strongly connected graphs. This is reasonable in many systems if the dynamics settle down quickly. And when this happens, the distribution will converge to some stationary distribution. We'll call this x star. And so what we're doing is we're solving for the x star such that that sets our set of differential equations to 0. Now let's note that for a strongly connected graph, the rank of the Laplacian is exactly n minus 1. And since the columns of the Laplacian sum to 0, this tells us that a row vector of 1s is a left eigenvector with eigenvalue 0. And this means that there's a corresponding right eigenvector row, also with eigenvalue 0. So this tells us that the solution that we're interested in is proportional to this right eigenvector row. So now we're going to do just a little bit of work. The Laplacian, as I said on the previous slide, is not full rank. That tells us that its determinant is 0. Now we're just going to write down the determinant expansion. And now I'm going to tell you a fact for Laplacians that you can prove for homework later, is that the jk minor is actually equal to up to a sign to the kk minor. Okay? So now just plugging in this fact into the determinant expansion, we can now see that the entries of the eigenvector that we're looking for correspond exactly to the solutions that we're interested in. So these eigenvectors, sorry, that's what I said on the previous slide. So the entries of the eigenvector are equal to the kk minors of the Laplacian. Okay, and so maybe some of you will know the following result. Kirchhoff's matrix tree theorem gives us a formula for these kk minors, and they are up to a sign, a sum over the spanning trees rooted at vertex k, where for each tree we just look at the edge labels. So these are the rates, and we multiply them. We write down their product. Okay, so this tells us that the entries of this eigenvector are homogeneous polynomials in the rates. Each of the spanning trees has n minus 1 edges, so the degrees of these polynomials are n minus 1. So we can write this down for our little example here. So we've enumerated the spanning trees. Here is the solution using the matrix tree theorem. Each of the entries.
Homogeneous or also multilinear?
Sorry?
Multilinear polynomials, right?
So they're multilinear in the edge labels.
Right.
But then it says the sum of the edge labels may have proportional to the concentration factors. So that's what
Yeah. Okay. So we'll look at the rates in just a second. And then all we have to do to get the steady state solution that we're interested in is to normalize. Yeah. So these solutions are ratios of polynomials in steady state probabilities. And recall that gene expression level is proportional to the probability of the perimeter being able to bind to the state. So for the purpose of creating an example, let's suppose that in our picture, the promoter could bind to states 2 and 4. So then this lets us just write down the solution immediately. And so the gene expression level is proportional to a ratio of polynomials in the rates. We can remember this 1 over 1 plus some nice function expression. So this is the general form of gene expression for systems described by these Markov chains. Yes? Okay. So if you'd like to think about or see somebody solve this system, you can look for this upcoming paper. They actually wrote down the polynomials. Very good. And in that system, what were the functional forms of the rates? Well, four out of the 5 in this example were just constants. And then we had this one binding transition that was proportional to a concentration of free transcription factor lying around. And so there was a linear dependence on a concentration. We can actually have more complicated dependencies. I won't go into any of the gory details, but examples of this include things like dimerization, where for example, you would need 2 transcription factors to bind in solution before they're allowed to bind to the promoter. Okay? So just to wrap things up, we want to be able to connect this biology to our evolvability framework. So let's focus on, say, sequence mutations to the DNA. These can occur at the promoter regions, which are being bound by transcription factors and other molecules. And they could occur in the promoter regions that are regulating these upstream dependencies as well. So compositions of these systems is a sort of interesting thing to think about next. And as a consequence,
How about the regions that produce the transcription factor?
Yes, well, yes, those are also evolvable. Okay, and so what are these mutations doing? They're going to perturb the model by either, meaning the graph, they're going to perturb the graph by either adding new states, for example, adding a new site to the promoter region where a transcription factor can now bind. So we're going to change the rates by, for example, modifying the binding properties of either the DNA or some protein that's binding to the DNA. And we can remove states from the system, for example, by setting a rate to 0. And so hopefully this gives us some things to think about for the discussion session, which will be happening later this afternoon. Thank you.